The 7QC tools are simple statistical tools used for problem solving. These tools were either developed and introduced to Japan by the quality gurus such as Naming and Jun. In terms of importance, these are the most useful. Kaoru Ishikawa has stated that these 7 tools can be used to solve 95% of all problems. These tools have been the foundation of astonishing industrial resurgence after the Second World War. The following are the 7QC tools: Pareto diagram, cause and effect diagram, histogram, scatter diagrams, component replacement, 5-why analysis and process flow diagram. The problems you face can be large or small, simple or complex, and easy or difficult to solve. Regardless of the nature of the problems, a fundamental part of every employee's role is finding ways to solve them. Having tools to solve problems and being a confident problem solver is important to your success. Problem-solving tools are determined by the requirements of the problem and the amount of time to solve the problem. Let us now learn the tool called the fishbone diagram. Assume you are studying a problem and you have identified a set of causes to the problem. The symptom or result or effect for which one wants to find causes is put in the box on the right. At each stage questions are asked and an answer is logically derived. Care should be taken not to directly jump to the root cause. The analyzer should now ask the question why, and the answer to this question is linked to a main group at a higher level. This may be man, material, machine or methods. First, the symptom or result or effect for which one wants to find causes is put in the box on the right. This is the discussion point, and the effect in this analysis is the reason why we are studying this in detail. The analyzer should now ask the question why, and the answer to this question is linked to a main group at a higher level. This may be man, material, machine or methods. Though it is not standard to group like this, it is good to start this way. The lighter boxes at the end of the large bones are main groups in which the ideas are classified. This could be sometimes identified as a cost code for the cost of quality computation. This helps in identifying the dominating group that impact the quality in the organization. Again, asking the question for these main groups, a set of factors that impact the effect is studied. The causes and its factors are identified and entered as branches to these main groups. The sub-reasons or sub-factors are linked to the factors. The factors are now subdivided into level, and how a change in the level to the factors impacts the final cause of the problem is identified. The fishbone diagram, also referred to as the Ishikawa diagram, because Kaoru Ishikawa developed it, and the fishbone diagram, because the complete diagram resembles a fish skeleton. Here is another sample of the cause and effect diagram. The diagram illustrates the main causes and sub-causes leading to an effect, symptom. It is a team brainstorming tool used to identify potential root causes to problems. Because of its function, it may be referred to as a cause and effect diagram. The causes of the effect are then laid out along the bones, and classified into different types along the branches. The Pareto analysis is a statistical technique in decision-making that is used for the selection of a limited number of tasks that produce significant overall effect. It uses the Pareto principle, also known as the 80-20 rule, the idea that by doing 20% of the work you can generate 80% of the benefit of doing the whole job. In quality improvement, a large majority of problems, 80%, are produced by a few key causes, 20%. This is also known as the vital few and the trivial many. Pareto diagram is a tool that arranges items in the order of the magnitude of their contribution, thereby identifying a few items exerting maximum influence. This tool is used in SPC and quality improvement for prioritizing projects for improvement, such as prioritizing setting up of corrective action teams to solve problems or identifying products on which most complaints are received. Consider an example in where the list of problem areas in a car are identified. The issues or concerns are listed in descending order of their occurrence. First, a histogram of the issues areas are plotted. Then a cumulative occurrence of this is plotted. The 80% point on the cumulative of the occurrence indicate where the problem areas are concentrated. This is by just 5 areas. These are the 20% that impacted the 80%. The 20% of all areas: transmission, fuel, instruments, engine and noise contribute to 80% of all concerns. What is the shape of your data? Knowing the shape of your data is as significant as the measures like mean, median, etc. The shape of the data set helps in identifying any obvious errors and outliers that may be removed and the measures recomputed. The shape also helps in determining the spread in the data. An important aspect of the description of a variable is the shape of its distribution, which tells you the frequency of values from different ranges of the variable. A data analyst is interested in knowing how well the distribution can be approximated by the normal distribution. A simple study of the shape gives a fair idea about the data's approximation to normality. Histograms or frequency distribution diagrams are bar charts showing the distribution pattern of observations grouped in convenient class intervals and arranged in order of magnitude. Histograms are useful in studying patterns of distribution and in drawing conclusions about the process based on the pattern. The histogram is normal if the highest frequency is in the central group and there is symmetrical tapering on either side of the central group. The natural or normal distribution would indicate that the process being studied is under control. A histogram with an unnatural pattern may indicate that there is possibly something unusual with the process, but is not an evidence of a process being out of control. For instance, a histogram depicting the distribution of age of all citizens will not peak at the center. It will start with a cliff tapering gradually till around the life expectancy, then dropping a little faster and once again tapering into a long tail. Upon studying a histogram, the following can be immediately inferred. Where is the process output concentrated? What is the spread in the process? Is the process performing within specification limits? What are the outliers in the process and how to set controllable limits? If action needs to be taken on the process, what action is appropriate? Is the assumption on the distribution of the variable correct? When solving a problem or analyzing a situation, one needs to know the relationship between two variables. A relationship may or may not exist between two variables. If a relationship exists, it may be positive or negative, it may be strong or weak, and may be simple or complex. A tool to study the relationship between two variables is known as scatter diagram. A relation expressed in correlation coefficient is between -1 and +1. The extremes mean high correlation or relationship. When solving a problem or analyzing a situation, one needs to know the relationship between two variables. The correlation consists of plotting a series of points representing several observations on a graph in which one variable is on x-axis and the other variable in on y-axis. If more than one set of values are identical, requiring more points at the same spot, a small circle is drawn around the original dot to indicate second point with the same values. The way the points lie scattered in the quadrant gives a good indication of the relationship between the two variables. Correlation need not be between two variables. It shall also be across several elements. Here is the example of data from manufacturing and the different kind of defects. The relationship is studied across all variables. Thus there could be a relation between total produced and the fan bending problem. This leads to a matrix kind of correlation. Any value above 0.6 and below -0.6 is critical for analysis. Component replacement. This method is used to find subsystems that is source of the failure or problem. In this case, while studying a bad system, a good system should also be studied. This is done by replacing one component or subsystem at a time and study if the effect is consistent across both the good system and bad system. Component search is part of statistical engineering, as developed by Shainin, is a contrast-based approach to problem solving. Statistical engineers ask what's different rather than what's wrong. They look for the largest source of variation, not all possible causes. They avoid identifying lists of potential variables until the convergent process has substantially narrowed the possibilities. Use this method to find the subsystem that contributes to the problem and also to identify the source of this problem. In this case, the what, where and when is compared to both the good and the bad subsystem. By doing so we shall understand what is good with the good system and what is it that contributes to the bad. Consider component search on an electrical part with several subcomponents, by swapping the good subcomponents with bad parts and also by replacing bad ones with good subcomponents. Their results should vary based on the output. This should also be repeated on many samples. In this case 10 samples are studied of both the good and the bad part. Thus it is clear that when the part P is included in the rejected system the output is high, while it is low when this part is not included. Similarly, now study the good system and replace with the problem subsystem. The output is seen as low. This concludes that this subsystem is a potential part to study further. Consider a situation where you only use the word why 5 times and try and reach a root cause to the problem. When something goes wrong, we tend to see it as a crisis and seek to blame. A better way is to see it as a learning opportunity. Not in the existential sense of general self-improvement. Instead, we can use the technique of asking why 5 times to get to the root cause of the problem. The 5 why is a useful exercise to track a single line of cause and effect, but it seems to lead to a causal factor rather than a root cause. Process mapping is a tool that is used to understand, analyze and document processes and activities in an organization and assist in identifying opportunities for improvement. A proper process map is like a strong foundation for Six Sigma project, and to be successful, a process map displays the sequential steps involved in converting a specific input into the required output. A map is a visual representation for the team leaders or an entire team's thoughts, ideas and questions relative to accomplishing the project goal. It should be one of the first tools employed when starting any Six Sigma or process improvement project. The map presents a structure of information and helps a team progress through that make process. It is a living document that will change throughout the project and has no set format. The process map can be used to drive specific actions and select the Six Sigma tools that should be employed early in a project, as it ensures that nothing is left out or missed. It is an effective tool for ensuring all potential questions and issues of a project have been both identified and addressed from the beginning of a project to completion. The following are the steps in development of a process map. The 7QC tools are simple statistical tools used for problem solving. There are several tools that you will learn as you go through this program. The 7QC tools is one set of such set.